Hello and welcome to the 11th episode of the RockyTerrain podcast. Today is April the 15th, 2021. My name is Thomas and with me as always is Dennis.
Hello there.
In today's episode, we are going to talk about lunar tectonic, so the field that I wrote my bachelor thesis on.
Hey.
But yeah, finally. But before we will do that, I would say, are there any news from your side?
Yeah, actually, there is quite a bit of news from my side because I've read a couple of interesting papers recently, but before I get into that, I wrote the final exam of my bachelor's degree today. So, oh man, it's really a cool feeling. That's it. I mean, of course, this is only going to continue when I start my master's degree. That's just the nature of the beast. But for the moment, no more exams.
And it still feels amazing. Just to know, like, one other box is checked.
Yeah, absolutely. Just looking at the list of things you had to study for and the list of things you had to write exams about, it's sometimes I think it's really mind-boggling to look back at all of that. It's quite kind of unimaginable that you had to study all of that and that one memorized all of that. I think, yeah, when you started to study here in Münster, when you just started seeing all these exams, which you would have to write one day, one way or another, if you wanted to finish your degree, it was really overwhelming. Because, I don't know, at the start of my studies, I couldn't even imagine learning all that stuff that was listed on the webpage where you have to sign up for exams and stuff like that.
I mean, I didn't even understand like some of the topics.
Yeah. That was actually one of the most frightening things.
Yeah.
That you read the title of an exam and you couldn't even figure out what could possibly be meant by the title of the subject. And yeah, it's quite an uplifting feeling.
Definitely. Congrats.
Yeah, so much for me. I'm feeling pretty free right now, which is kind of a weird feeling because I've been studying a lot over the last few months. But what about you? What's going on in your life?
Yeah, actually, currently not so much. I mean, I have a lot to do currently, but I don't know, like nothing big news. The semester started again, so it's my second master semester. Had our first lecture today. I have now 2 projects in the Planetology Institute that I'm working on. So there's a lot of stuff to do, but not generally large news, I would say. Yeah. Today is the day where I'm like, nah, nothing really to talk about here.
Quick and simple.
Yeah, very quick and simple today. But as far as... Oh, wait, there's actually one thing. Ingenuity. The Mars rover, well, not the Mars rover, but the Mars helicopter, Mars drone. Yeah, so they actually wanted to start it like last Sunday, somewhere around that. But then there was like a technical problem, and now they're working on that, and there's like a script they have to update, and not earlier as tomorrow, so April the 16th, they want to try launch it again. I don't think that there is a direct date yet, but they said at least at April the 16th.
Yeah. Not even on Mars you're safe from updates.
Was a new Windows update.
Yeah. Yeah, no, I actually caught that. I was already wondering when it was going to launch, because I mean, I got that they delayed it several times, but yeah, didn't know that they really had a fixed date in mind by now. Again, maybe. I don't know. Was there actually generally a fixed date?
No.
Wouldn't really make sense either. Huh?
Yeah. They're just trying to see when they can do it, and then it's probably just be like a quick update after that they're gonna have a news session or something like that.
I mean, the stars have to align. Weather has to be perfect. I mean, you don't really want to launch the first helicopter on another celestial body and have it crash immediately.
Honestly, that's interesting. I don't even know if the weather on Mars varies so strong from day to day that...
I mean, in terms of dust storms or...
Yeah, but like dust storms are like, large events. That's not like one day there's a dust storm. That's something different. I wonder if there's if they have to see is the wind good today, or if the wind is on a steady state. I don't even know that. That's actually very interesting. I'm gonna look that up for the next episode, maybe.
Write it down before you forget it.
Oh, yeah. I'm just gonna the Mars weather forecast.
Is there something else scientific you want to talk about?
No, but I kinda recognized that you were really wanted to talk about, or you were really hyped about some pterosaurs paper, right?
Yeah, indeed. Actually, there are 3 pterosaur papers I know of dropped since the last time we recorded. One of them concerning neck vertebrae of a special gigantic pterosaur group, in terms of they were gigantic animals, and 2 papers describing new genera. And I think I'm going to maybe talk a few sentences about one of those new genera, because one of those called Kunpengopterus. Kunpengopterus.
Is this an ASA or?
Ja, da hast du mich jetzt wieder erwischt.
Oh, sorry.
Ich habe keine Ahnung.
Okay, wir reden einfach weiter.
Ja, schneid das mal raus.
Ja.
Kunpengopterus is a pretty special pterosaur, because, or maybe to give a very, very short introduction, because, I mean, you need to understand a little bit about pterosaur hands before, if you want to compare your arms to pterosaur arms. Pterosaurs essentially have 4 fingers, or factually, they have 4 fingers. They lack the pinky. The ring finger is the one which the wing membrane is attached to. And then they have the 3 other fingers, the middle finger, the index finger, and the thumb, essentially, which they walked on. They walked on all 4s on the ground. And what's usually pterosaur hands were reconstructed rather simple, but last year there was already a paper which pointed out that some certain pterosaurs had a different hand anatomy than others, and this new genus is pretty special because not only does it have weird hands, but it has a pretty special adaptation because it seems to have an opposable thumb, meaning that this pterosaur would have been able to grab things, which is commonly associated with climbing animals. And that's just really cool because, yeah, you're really slowly starting to get the sense that these leathery winged, quote unquote leathery, but these winged cousins of the dinosaurs are becoming more and more understood, because slowly you get the feeling that, yeah, there was considerable ecological diversity in there.
Yeah, and actually pretty cool diversity. I don't know, I like impossible funds because I have one, but just in general, it's a cool adaptation. It's really useful if you're climbing or using tools or anything like that.
Yeah.
And
actually, I saw the artwork from the paper before I saw that a new paper had dropped. And I was really confused because, one, there were two individuals shown on this artwork, on this paleo-art piece. Unfortunately, I don't remember who it's from. But one of them was holding an insect in its hand, in its left hand, and I was like, yeah, no. I was like, I was about to skip until I saw that there was a title of a paper about that, over that. Yeah, and when you look at the individual, it seems I haven't read the paper yet because I had to study. So I'm going to do that today, I think. But it's actually pretty cool looking. Looks a bit like one of those candy grabbers. They did it first. Pterosaurs did it first.
Yeah, no, that's a pretty cool topic. I'm glad you talked about that. And I haven't seen the images yet. I think have you sent me the paper? You've sent me one paper, but I haven't looked at it. But I will look at definitely after the podcast, because now I'm really interested in how that looks like.
Yeah.
Maybe we'll link the image in the on YouTube.
Yeah, or maybe the paper.
Or the paper, yeah, better. Okay. Anything else?
Nope. I think one pterosaur paper. I mean, I could talk about all three, but yeah, no, I think one should do it, because this was the most outstanding one.
Yeah, I cut it anyway. As always, I let you talk about your pterosaurs, and then in the end, I just cut it all out.
You know what's maybe the coolest thing? They could have given you a thumbs up.
Yeah.
One
Okay.
pterosaur like this. Now we can move on. Yeah. Now I'm confused. All right. I think then let's go into a small break and return with the main topic of today. And which
today's
is
topic, lunar tectonics.
I'm kind of in a good mood right now. I don't know. Do you actually remember back when we said in the first readings on planetology?
Yeah. Actually really good.
When it all started, when it all began. And I mean, actually that was, I think, why we started to come along very quickly after we truly got to know each other, was that you had a fascination for dinosaurs. But you wanted to go into planetary sciences because you were even more into that than paleontology. And with me,
at least at that point of time.
Yeah.
10 years before it would have looked better, but yeah.
Yeah, and with me, it was the exact other way around. I was interested in planetary sciences, but yeah, I want to get into paleontology. And after these first readings and after our exam on planetary sciences, it feels like things really took off for you, because through our professor you learned about the moon and potential future points of interest about the moon. And I don't know, for me, you have been the moon guy ever since, and I think you are for many of our friends.
Yeah, that's true. But I'm also working on Mars, and I said no, the Moon Mars guy.
No, you'll forever be the moon guy.
Yeah, and I can live with that. That's actually Moon is pretty cool.
Yeah, and you even wrote your bachelor thesis about something on the moon, and I think from now on you could elaborate.
Yeah, that's what I at least try to do. Yeah, so I'm not going to talk about my bachelor thesis itself today, but I'm going to talk about a topic which my bachelor thesis is about. And yeah, first of all, as you said, it was a great opportunity that my professor gave me there. He gave me my own project basically, and said, okay, so if you want to do something, there's a cool topic, so if you're interested in that, you're welcome to work on it. And yeah, I don't know, from the first time I've read it, just because I was so confused, I was directly sold. Kind of, the point where like the authors itself were like, yeah, we don't know. At that point, it was pretty sold. Yeah, and that topic is lunar tectonics. Now, first of all, what is tectonics? Now, tectonics in geoscience, at least, is the study of the crust of a planet, so the outer shell of a planet, and its state and its deformation, the physical stresses within this outer layer of a planet, and all the movements in there. So on Earth, there would be, for example, the formation of mountains. There would be earthquakes and all that stuff. That is part of the tectonics study. And what I have looked at, and many other people, is the tectonics on other planets, and specifically the tectonic situation on the moon. And therefore, I want to answer two questions. So first of all, what does it actually mean? So what kind of tectonics are existing on the moon? I mean, we know that there is no plate tectonics on the moon, so it probably doesn't have mountain ranges and anything like that. So what's happening there? So that's the first thing I want to address. And then a second thing I want to address is the question about when. Is it like long ago, or is it still... I mean, the moon seems pretty dead, right? It seems, compared to Earth, pretty inactive.
Yes,
and
that's it.
Yeah.
Goodbye, everyone.
Yeah, moon is inactive, but... No, the question is it actually? And is there maybe some activity going on that, yes, maybe more hidden from our eyes? And this is what I want to address today. But first of all, what kind of tectonics do exist on the moon? Then, as I said, most of tectonics on Earth are, because of plate tectonics. But on the moon, we don't have that. And therefore, we first have to understand how the moon formed. And I'll do this very briefly. We have a proto-Earth and a large body around 3.53 billion years ago crashed into the Earth. And because of this crash, a lot of material was thrown out of Earth. And this material now orbited Earth and formed our moon. And this means that our moon at some point was pretty much completely molten, at least the outer layers. It had like a completely molten magma ocean. Magma ocean is like the word that is used in geology. It had a magma ocean. And after time, this ocean, of course, cooled. And it solidified, it crystallized. And the first hard rocks on the moon formed. And this is now where it gets interesting. So first of all, what kind of tectonic activity can exist? We have compression, right? You have a material and you compress it together, like a block of concrete, and you press on all sides together and try to smash it. you can have extension. You have one block and pull it apart. And then there's something like transform, which I'm not going to talk about today, but you can imagine like two blocks moving relatively to each other, like one to the right and one to the left side. But the important part for the moon is extension and compression. So, extension. What kind of extension do we have on the moon? On the moon we see graben. These are large structures that can be several thousand kilometers long and some kilometers wide. And they are all very old. They're at least older than 3.6 billion years. And then, after 3.6 billion years, we basically see no large graben anymore. And actually, this makes sense, because 3.6 billion years ago, a very long time ago, the moon was still very hot. It started to solidify, it started to crystallize, and the first crust started to form. But it was still extremely hot. So there was still a lot of movement of material, and then extensional forces can exist. But once the moon started to cool down and cool down and cool down, then something else happened. Because cold object has less volume than when it's hot. So by cooling down, it shrinks. And by shrinking, it of course then experiences compressional forces. And around after 3.6 billion years ago, we say that the net extensional force of the moon transformed in a compressional state. The moon went from having a lot of extension to getting so cold and cold and cold that it started to be dominated by the compression of the cooling of the moon. So that's why we have extensional forces that are older than 3.6 billion years, and then it was the time of the compression on the moon. And for compression, we basically have two kinds of features. There's maybe a third type, but I want to talk about the two types that are interesting now. The first are low-bed scarps. Now, therefore we have to understand a bit more about the moon. When we look at the moon, we see two different kinds of colors. There's like the large light gray areas, and then there are like these dark spots. Now, these dark spots are basalt. These are large impact basins, very, very old, that were then later filled by volcanic activity. So new hot material, new hot lava erupted and filled, after time, these large impact basins. So these are layers of basalt, a lot of layers of basalt. And they are called maria because people first thought that this could be oceans, and that's why they're called maria. And then we have the light gray areas, the lunar highlands. Now they are made out of anorthosite. And for a very simplistic explanation, these are basically just one block. This is basically just one block of material. These basaltic maria, they are layered, like a lot of layered basalts. But light gray areas, this is just basically one rigid block of material. And in these highlands, low-bed scarps exist. Now, low-bed scarps are very, very simplistic tectonic structures. These are basically simple thrust faults. To get maybe a picture in your head, imagine you have a block of concrete or something like that. And then you push it on two sides. Push it together. And of course, at some point, it will crack. At some point, the force is so strong that it will crack. And there will be fractures. Some linear fractures that will appear throughout the block. And then, if you press now further, these fractures are weak points. And along these fractures, there can be a movement of these now splitting blocks. Right? On these fractures, now one block will apparently move on top of the another. You will press it together and together and together, and the surface area is shrinking and shrinking and shrinking. You press it together. Yeah.
All that stuff has to go somewhere.
Right. And it goes on top of the other.
Yeah. Because it's the easiest way.
Yeah. So the surface area that was before on top is shrinking, basically. And this is very simplistic kind of rust fault. And that's what low-bed scarps probably are. There's like one large fracture and rust fault that is located to some kilometers deep in the highlands. And due to compression, there's one part that moves on top of the other part. And they are basically scattered throughout the highlands. They were first noticed with the Apollo missions. So when we had the first, because they're very small, and so we had now with the Apollo missions the first like more high quality images of the surface of the moon. And then these structures were found. And then we have one other structure, compression structure. And these are wrinkle ridges. Now, wrinkle ridges are located within the lunar maria. And they are a bit more complex. And the whole structure itself is like a very difficult field where there's a lot of discussion. But the important part is they are a bit more complex. They are not just simple thrust faults. Actually, we don't even know how many thrust faults there are involved. There are some people that saying there are like 3 or 4 thrust faults involved. This would be like very complex. But a very important part is following. As I said, these maria are layered. And that means that you cannot just have a simple thrust faults where one block is moving above the other. As like in this one block scenario with the highlands. And the reason for that is actually very simple. Just imagine you put some papers on top of each other, like a stack of paper. And now you bend it. Like you bend it so there's like in the middle a settle or something like that. Then, of course, there will be a movement in between these papers, right? In these individual sheets of papers. They will move in some sort relatively to each other.
Yeah.
And it's the same case here. Like these layers, these connections between different layers are weak points. There's not solidified in between these layers, or like on a more weaker scale. And that means that these will move relatively to each other. And that's why, in addition to a thrust fault, the material will bend. It will fold. And that's the case for wrinkle ridges. So wrinkle ridges do consist of a thrust fault and a bending and folding of material. And that's why they look a bit more complexer. They have like this broad arch and broad topographic linear rise. And then off top of them is like this small, steep ridge located. Very difficult to explain, but as I said, it kind of look complex. And they do not occur randomly. They have some weird patterns that we can observe. So most of the basins have like a circular structure because they were old impact basins. And when we see these wrinkle ridges, then they form concentric to the basin, like in large rings. And then there's some that are radial. And some points are linear, like all in a north-south direction, for example. So they're not scattered randomly throughout, but they seem to be orientated. And that's pretty interesting. And I will talk about that in a second. So these are the two types of compressional forces on the moon. And now we have to ask ourselves, why do they form? Well, I've said we have compression, the moon is cooling down, and due to the cooling of the interior, the moon is shrinking, and due to the shrinking, we have compression. And compression due to the global cooling of the moon would result in randomly distributed forces. There would be like no orientations and patterns visible. It just would be Like everything is compressed everywhere. It would just result in randomly distributed structures. And that's what we see with flow-based scarps, right? They're like everywhere, and they seem to be randomly at least. So that seemed to be the case. But as I said, wrinkle ridges, no, they follow patterns. So there has to be something else involved. It's not just global compression. There seemed to be another factor. And this is subsidence. These mare basalts are heavy. Basalt is a very heavy rock. It's very dense, it's very heavy, and it's more heavier than the highlands, the anorthosite, the rock of these light grayish areas. And this means that all the basalt is pushed down to the middle of the moon due to gravity, stronger than the light material around it. It's pushed to the center.
Pulled.
Very strongly. Pulled, yeah, you can say pulled, but yeah. I wanted to say push it because maybe easier to understand that.
I get it, but
yeah. it's pulled to the center. Yeah, it's much nicer to say that, pulled. It's pulled to the center. And, well, that results in all the material is like additionally compressed because it all tries to move to the center of the moon. And this is called subsidence. And this is why we probably see these concentric and radial wrinkle ridges. Like if there's modeling of how the forces would react in such a scenario, then it says us, there should be like different throughout these, circular basins basically. There are like areas where there's contraction, and then there are areas where there's extension, like at the edges far outside. And this is exactly what we see. There are like these graben that are like far outside, because if you push some material into the center, then of course somewhere else material has to be taken away. And so we have this graben on the outside, and then we have in the center this concentric wrinkle ridges. I hope it's an understandable image. I've looked at these things so often, I just know how they look like. Yeah.
So maybe let me try to summarize, just to have a look whether it worked.
Yeah.
So basically, these structures are concentric, and they are concentric simply for the reason that the basalt is pulled towards the center of the moon because of gravity. The way the stresses work when this happens is that concentric fractures form. Yeah, and of course at the edges the material is basically pulled towards the center, pulled towards the bottom of the mare, and therefore you have extensional features on the edges of the mare.
Yeah, exactly.
Yeah. So it's not randomly orientated, and there's the explanation for that.
Correct. Very good.
See, I could be a planetary scientist after someone explained it to me.
Yeah, but that's always the case. You need someone to explain to you.
Yeah.
Yeah, but as I said, there are also some other patterns, so it's much more complex. There are probably many factors involved, as always, but this is like the main factor that we think is involved. However, if we look at the timing, we do have some evidence that this happened only, around 3.5, 3.58 billion years ago. And after that, it seems to be the case that global contraction was much more dominant. 3.55. I hope I said it, but 3.55. And after 3.55 billion years, it seems to be that global contraction was much more dominant and subsidence played a smaller role. It's very difficult to say. And I know that there's some newer studies who try to see how much subsidence there could be, maybe still even today. But like the one paper that basically everyone is referring to shows at least some strong evidence that seems to be after 3.5 billion years, global contraction was much more dominant. And I will not go into why, because that's very difficult. And it would like be too much for the episode today. But that's our case. So these structures are probably very old, right? They're probably some 3 billion years old. And it's also what some studies have shown. They try to see or they try to get the ages of these ring creatures. And they have also shown that at least most of these structures seem to be older than 3 billion years. However, there are some areas where this does not seem to be the case, which again shows how complex this topic is, and which again also shows that, or in this scenario, could also be two different methods that were used, and it's an active field, and that's also the field that I was working on. But in general, these are thought to be very ancient structures, very early on in the history of the moon. But they're formed like it seems for a pretty long time. There is also evidence that some of these ring creatures formed some 1.2 billion years ago. And I know that sounds pretty old, especially for a paleontologist like you.
Yeah.
But that was not meant as a assault. I mean, on Earth, like most of the things we talk about are pretty young, like some, I mean, young in quotes. I mean, they're like 800 million years, 500 million years. It's actually pretty old. But on the moon, like 1.2 billion years is actually quite young.
Yeah, I mean, it's two completely different things, because Earth is a way more dynamic place. Tectonics work way more intensely on Earth's surface, or tectonics on Earth reform Earth's surface more continuously than on the moon.
Exactly. There's, of course, a difference. Yeah, but that's the case where we stand at like for a pretty long period of time. These structures, these ring creatures seem to be pretty old, some 3 billion years, and some individual of them maybe even 1 billion year old, and they form probably mainly due to subsidence. However, that's like the basis that I wanted to have. Like, what is lunar tectonics? What do we see there? And why did it form in the first place? And now to the question again, is the moon actually so inactive as we think? I mean, if we look at the moon, it seems so, because it looks the same every day. And it probably looks the same since many, many years. There's no real change. There's no atmosphere or an hydrosphere, like oceans and rain and weather, that reworks the surface. There are no plate tectonics, so there's not the formation of new material, and on the other side, the elimination of material. There's not a formation of large mountains. There's no active volcanism anymore, at least as far as we're concerned. So, is the moon basically inactive? Well, we kind of talked about the topic in one episode before, and that's the episode about the Rocky Archive. So, archive. I think episode 2 was that, right?
Yes, indeed.
Yeah. But we already talked a bit about that, and we already kind of hinted that that's maybe not the case. Of course, the moon is not as active as Earth today. That's very easy to say. And it's probably also not as active as, for example, Mars or Venus. But there is some sort of activeness, and if this isn't tectonic activity, that's what I'm trying to explain now. the first hint of a maybe still active moon we had with the Apollo missions. Now, I've told you that they had like the first images of these low-bed scarps. And the interesting thing is, these low-bed scarps on these images look crisp, like sharp edges, crisp morphology, very easy to see, very dominant. And that's interesting. Because there is an erosion on the moon. It's very low-key and not comparable to Earth, but there is. To get some number, we say that there's like movement of material of around 3 plus minus 2 centimeters per million years. Which means if you have like a bucket that is 1 meter deep and you like bury it halfway to the ground, then it will be filled after, 50 million years.
Oh man, that's just ludicrous, but it occurs. That's the key point.
Exactly, it occurs. And it occurs actually on so slow rate that you can kind of compare the appearances of different structures to get like an idea of relative ages.
Yeah,
And because,
main factors involved are solar radiation.
Yeah.
What else? Something?
Micrometeorites.
Ah, yeah, all right.
Yeah, solar radiation, micrometeorites,
Yeah.
that stuff. And one additional factor, which I will get to in a sec. But we saw, or not we, but the scientists back then saw that these structures looked very crisp. And so they asked themselves, how old can they be? And then the first calculations were done. If we say that the moon was completely molten, at a completely molten magma ocean before, how would the forces be today? Would this still be possible? And the first calculations have shown, yes, indeed, to a certain degree, like very shallow activity, very surface activity, could actually still exist. This was very early studies, very early calculations, but it seemed to give a first hint that it could be still possible. And then the Apollo missions did something else. 4 seismometers were placed on the surface of the moon by the Apollo missions. So, seismometer is, recording the movement of the Earth, basically, of the surface. And it then records earthquakes here on Earth. And on the moon, we call them moonquakes. I've not known that before. Before I
real
studied.
Creative.
Yeah. And on Mars, Marsquakes, yeah.
Wow.
Anyway.
Quality content.
Yeah. We placed 4 of them on the moon. And, we have recorded moonquakes. Which is, of course, very interesting.
Can you say in how far they're comparable to earthquakes? So in terms of strength, intensity?
Yeah. I can. So let's start with that. They have like a magnitude, or like the largest magnitude was slightly above 5 on the Richter scale. So like it's not like a very weak earthquake here, but it's like also not very strong. You know what I mean?
But you would notice it.
Yeah, definitely. You would definitely notice it.
Yeah.
And then, but it's very difficult to say. Moonquakes react a bit differently than on Earth, than earthquakes. Yeah, and then the next question is, why are there moonquakes? Could there be impacts? Like it's maybe just meteorites crashed onto the moon's surface and we recorded that. And we can actually compare this then to like real impacts and see if this is an impact or not. So this was a lot of work was involved. But in the end, we are pretty sure that we recorded 28 surface near moonquakes. There were also some recorded very deep down within the moon due to completely different reasons, which may be interesting for a later time. But for now, 28 of them occur very near to the surface. And these other ones, well, that probably seem to be related to lunar tectonics. Some movement in the crust. And movement in the crust is by, per definition, the study of tectonics. So we had now two ideas, two hints for more recent activity. We had these images of these very sharp structures, and now we also had the recordings of moonquakes. And so there also it was tried to like localize these moonquakes to see where exactly they happened, and this also seemed to correlate with some lobate scarps. So actually very, very early on, people had the idea that there might be maybe an activity ongoing. But the idea of a recent activity actually really started to take speed in the last 10 years. Basically with the launch of the Lunar Reconnaissance Orbiter in the year 2011. Because the Lunar Reconnaissance Orbiter allowed now on global coverage of images with a resolution of up to 0.5 meters per pixel. So every pixel displays half a meter. And this, is an incredible high resolution and much better than anything else we had before. And with that, we were able to see that these lobate scarps are actually everywhere. There are many of them. Like incredible many of them. And they're scattered all around the moon.
Yeah, that in and of itself is pretty amazing.
Yeah. And they're very small, so they're probably even more than we know of now. There are maps of them. And, they have like mapped over 5,000 of these structures. Nevertheless, with these images, we also found some other evidence for a possible ongoing activity. So again, they had these sharp morphologies. Like that's always a good first hint. Then we looked at the crater population. So how many craters are on these surfaces? Ideas, an old surface has, of course, many craters because it's very old. And a young surface just didn't have enough time for many craters to form, to meteorites hitting the surface. And that's why younger structures have less craters than older structures. And when looking at that, it also seemed that at these lobate scarps, crater populations were not as dense. And the idea was, if there's like a movement, then there's of course a moonquake, and a moonquake could destroy some of the smaller craters. Then we saw boulder fields. These are areas where a lot of large boulders are exposed, some several meters to tens of meters in size. And the question is, how did they get there? Where do they come from? Boulders can be found everywhere on the moon, mostly due to impacts, because impacts, of course, throw material out. But now we see them at these lobate scarps. And later, we find them also on some ring ridges. So the question is, how do they get there? And the idea is, if there's movement, like shaking due to a moonquake, then all this dusty material on the surface of the moon, which is called regolith, very fine-grained material, will well, move down in fractures, you know what I mean? Like the ground is moving and all this fine material is moving down through fractures. Like if you have a glass full of cornflakes and there are like some broken cornflakes and some from back of cornflakes. And when you open it the first time, you will see that all the small stuff is at the bottom and all the big stuff is on top, because the smaller stuff is moving through the small fractures in between.
So basically the small stuff is sinking below?
Yeah.
It's basically, yeah. I think the cereal example is a good one. If you have a cereal consisting of differently sized grains, if you shake it, what will happen is that slowly but surely the small stuff will sink to the bottom. That's exactly what's going on here. So it would basically, that's pretty interesting, because I mean, just getting to the conclusion that this could be what's going on is pretty interesting.
Yeah, that's also why it. I mean, it's still very there are many papers coming out right now to talk about these things, and it's still debated, because we can see these boulder fields everywhere on the moon. You know, this does not necessarily mean that they have to be occurring everywhere because of the same reason. But yeah, so we still have to look into that if that's really the case. But this high abundance of these boulder fields at low bed scarps and ring ridges is at least a very good idea on what could be going on.
I mean, you showed me pictures of them.
Yeah.
And for the listeners, they really they look out of place. They really look out of place, because on satellite images you can really see these big boulders just standing there. And it just, especially if you know a bit more about geology and the way sediment is transported, and knowing about the fact that the moon is rather inactive, because I mean, there are such occurrences on Earth where you have big boulders laying around in an area otherwise devoid of other sediment, but this usually occurs when wind just blows away small particles, and this is not what could be going on Earth, on the moon, excuse me. So the first time I saw that, I couldn't really find any explanation how this could have come about. I mean, I'm not familiar with planetary sciences, and of course we're just students, so we don't claim to know enough to explain such things, but it was just from the basic geologic understanding we got during the bachelor's degree. I couldn't really wrap my head around it.
Yeah, I know what you mean. The first time I saw them, I haven't even like really recognized them. It's just, oh yeah, they're both there. And then at some point, I was like, wait, why? Why are they there? Yeah, they really look out of place. And that's the idea behind it. But some people say, you know, that there could be also, the movement does not necessarily have to do because of their like tectonic activity. Maybe an impact, you know, could have made that. So there are some other ideas how that could form. But at least I think of what I've seen and so on, the high abundance is pretty striking, you know.
Yeah, I remember that as well.
And yeah, how could this help us get an idea of the timing? Well, as I've said, there is some erosion on the moon, on the surface, and now we do something very similar. We try to think, how long could these boulders survive on the surface till they are broken apart? How fresh are these boulders, you could say? And it turned out that, well, these boulder fields could actually hint that these boulders should have been excavated within the last 100 million years. And if we now say they were, they formed because of a movement, because of a moonquake, and therefore they would be an evidence for tectonic activity, then that would be also an evidence for tectonic activity within the last 100 million years. So this was like the idea with the boulder fields. And then something else was found. From, I think the first time this was found was from Waters et al. In 2012. And what they found was small graben. Now these graben are like some meters wide. They can be like even smaller than a meter wide. Some of them are some 10 meters wide. And they have lengths of around some meters to some several of meters to some 100 meters. So they're still very small comparing to all the other structures on the moon that is pretty small. Very, very small. And I've told you now before that extension was not a thing after 3.6 billion years. The question is, am I lying to you?
Of course you are.
Of course, yeah, always. But not in this case. These graben were only found near, or at the beginning, only found near lobate scarps. Nowhere else. Just there. Only there. Directly in the back of these structures. And so the question was, why? We don't have extensional forces on the moon, so they have to be very regional. They have to be like small regional forces that seem to be extensional in some sort. And what is it, a region? Well, these lobate scarps. So then the idea was, well, if you push material on top of each other, a shortening of the surface, you also have to take material from somewhere, right?
Yes, indeed.
And then to the flexural bending and all that that's happening in the back of these scarps, these graben could have formed. And that was incredibly interesting. And then, well, as I said, these graben are very small. And also they're very crisp looking. Extremely sharp edges. So same question. Well, how old are they? Now I've told you that if you would bury like a barrel that is 1 meter deep into the surface, it would take like 50 million years to be filled up. And some of these graben are less than 1 meter deep. So they should have formed at least within the last 50 million years. And if we now say that they actually formed because of the movement of this underlying thrust fault, then, of course, they're also evidence for this tectonic activity. And therefore, like, more and more stuff seem to be found that says, well, there could be a tectonic activity within the last 50 to 100 million years. Now, this, of course, still seems pretty old, but on the moon, that's recent.
Yeah.
That's actually so recent that you're basically gonna say, yeah, then it's probably still happening. Like all of these papers end with, yeah, probably today also, because 50 million years, why would they stop now?
Yeah, I mean, just look at the scale. If it's been going on for billions of years, it would seem pretty unlikely that we are just existing in this perfect little time frame.
Yeah.
Where it just recently stopped.
Yeah, exactly. So that's it. We have the evidence. Now we can say, okay, global contraction seems to still form these structures. Finished. But of course, as always, it's not that easy. tectonics is a very difficult field because there are many, many reasons involved. It's not as simple as always to say like, okay, that's the reason, let's go. There are so many factors involved just because nature is very complex in many scenarios at least. And in this case, we found something strange. These lobate scarps are scattered all around, the moon. And I've told you before, global contraction, results in randomly orientated structures. And that seemed to be the case. But now, since we have found so many of them and we mapped them, we see that that's not the case. They are not distributed randomly. There are patterns. So, what does this mean? Well, we know that global contraction, the cooling of the moon, would result in randomly orientated patterns. And that's not the case. So, there has to be an additional factor involved. But what could that be? Now, in a study from 2019, 2020, also from Waters et al., tried to look at that. And what they've done is they looked at the data from the Apollo missions on the, moonquake data. And they first of all tried to relocalize these possible moonquakes to get like a higher resolution. But that's not the important part. The important part is that they try to look at the timing of these moonquakes. So when did these moonquakes happen? And over the years. So these seismometers were active between 1971 and 1977, something like that. And now they wanted to see when did these moonquakes happen, already like randomly or were there some patterns visible. And actually there were some patterns visible. So, as you may know, the orbit of the moon is not perfectly circular. It is evolving over time. It's an ellipse and it's evolving over time. And because it's an ellipse, there is a part where the moon is very close to the Earth and a part where the moon is very far away from the Earth. If the moon is very close to the Earth, we call it a perigee. And when it's very far away from the Earth, we call it an apogee. There's like a distance between some 40 to 50,000 kilometers range. And we see that from these 28 moonquakes, 18 of them happened when the moon was pretty far away, so near the apogee. And that's interesting because that's not randomly distributed. That seemed to be like a pattern. And if we do models, we see that the forces, the tidal forces on the moon, so the tidal forces between Earth and moon, are the strongest when the moon is far away from the Earth and then again pulled closer. That is where the tidal forces are the strongest. Okay, so there seem to be moonquakes that are pretty common when the moon is far away. Now let's look at the patterns that and possible influence by tidal forces would result in. And they fit pretty good. There are still some parts where there's like, some does not fit as good as some others, but overall, the patterns fit.
It's too much to neglect it.
Yeah, definitely. So, the idea is, could there be additional factors? Like, okay, the overall force is, of course, global compression. The moon is cooling down and everything is pulled together. But the question that this paper asked is, tidal forces an additional factor? And it seemed to be yes. From the data that we have now, yes. It seems that we get closer now to an idea whether today's what today's stress field of the moon looks like. And we are not yet very close to like the true stress field, just because it's so difficult, it's so complex. We have tidal forces and compressional forces due to cooling, but there are of course many other factors involved. Like the moon, for example, is slowly moving away from the Earth, very slowly but steadily. It gets farther and farther away to the Earth, and this also influences a possible stress field. And then we have a possible influence of the sun, the tidal forces. That could be also an influence. Then we have some regional stresses that could influence. So there are many other factors probably involved. And now with that, I want to kind of get a bit to the topic that I've worked on. I will not explain exactly what I've done because this would take longer. But I looked at ring curvatures within one of these maria. And I tried to get an idea when they formed. And what I've found is a wide range of these ring curvatures. Like these structures that were actually thought to be very ancient seem to have formed, yes, very long ago, but also very recently. The same evidence that we found on these lowbed scarps, so these graben and boulder fields and all that stuff, I can also see that with ring curvatures. And other people have found that too during the last 1 or 2 years. More and more paper come out that looked at other areas on the moon, and they have found exactly the same. These ring curvatures seem all to be active. And this is again a whole nother topic to itself, because why? Global contraction? Probably. But what else? What additional factors are involved? Well, maybe tidal forces again. Yes. But also maybe other forces like subsidence. We don't really know what the influence of subsidence today is. Maybe there is some influence. We don't know. Maybe some weird regional stuff. Maybe some stresses that are very deep, located very deep in the moon. Some people say that that the moon is still not in an, what do you call it? Ein Gleichgewicht.
German word of the day.
German word of the day.
Equilibrium.
Equilibrium, right. That's the word I was searching for. German word of the day. Yeah. Gleichgewicht. The equilibrium. Some people say that the moon is still not an equilibrium on a stress level, and they're still in the inner, very deep in the moon, there's still forces that try to get the moon into an equilibrium. And maybe these stresses have an influence too. The point is, we don't know. We have a good idea, or we have now many evidence that the moon is still tectonically active. We also have some evidence why it is tectonically active. But there seem to be so much more factors involved. And that means that there's still a field where a lot of work has to be done. And probably we're not nowhere close to a real answer that is very close in our future.
It feels like one of those cases where right now people are at the point where they start to notice that, an old view has been wrong. It's this thought many people have that the moon is just this completely dead object, that it's just this inactive celestial body out there circling the earth ever so gently. It just doesn't fit.
Yeah, and that's like one of these cases where more and more stuff is found that you just haven't known before. Like we find something new that is kind of weird, and then this leads us to a complete another topic, something completely else, where we are like, oh, now we understand that. Yeah. And then something else is found that seems to be weird. It's like an ongoing process of finding new and new and new and new stuff.
I mean, especially this topic with the tidal forces, once again, I'm not in that field, but wouldn't you expect these tidal forces to have some sort of effect anyway? So I'm just curious. I would have thought that this would have been thought of earlier.
I mean, yes and no. We know that that's a case, for example, for the moons of Jupiter and Saturn, just because Jupiter and Saturn are so massive. The moons of Jupiter and Saturn are basically squeezed. They're tortured by the gravity. They're tortured so strongly that there is still active volcanism on these moons. Not because of the interior heat, but because they are stretched so strongly. But in the case of the Earth and the Moon, the Earth is not the largest object. And the Moon is actually pretty large too, compared to Earth. So that there are some tidal forces, of course. I mean, we have tidal waves on Earth. But there seem to be no... To that point, we haven't found any correlation, I think it was generally thought it's just not strong enough. I'm pretty sure that wasn't people's mind before. Pretty sure. But it just seemed not strong enough. And there was no evidence to suggest it,
Yeah. I mean, I didn't want to sound arrogant or anything.
No, not at all. It's a very legit question. I mean, it's a very legit question.
I was just wondering, because I don't know, it's these tidal forces, it's something, again, from our perspective, this is something people have started working on in recent decades then, and therefore it feels so given to us that, yeah, of course, there's tidal forces, but then again, we just started to learn about that stuff a few years back from our personal perspective, so... Yeah, but honestly, it's really interesting, and I just love these cases where, we start to see that maybe it's more complicated than we thought before, and in this case, it's nice to see that this gray, seemingly boring neighbor isn't so boring after all.
Yeah, and it's very interesting for our future, because we will go to the Moon again. I mean, if it's now 2024 or 2026 or 2028, I don't know, but we will go there again at some point. And then we have to see, well, first of all, what do we want to do? What science we want to do? And, well, having new seismometers and new up-to-date seismometers. Maybe even, some radar, radar observatory or something like that. Radar, yeah, that's why I was confused. Radar. Some radar observatories to get an idea of the subsurface structures of these things. These are what we have to think of now, and I think we have good evidence that supports that we need more data. And also, on a completely another level, a risk evaluation. Because up to that point, we probably wouldn't have bothered just to land. I mean, we have landed very close. Apollo 17 has landed very close to a low-bed scarp. But now that we know that there could be moonquakes up to 5 at the Richter scala, that means that maybe we should get at least in some sort of safe distance with our stuff.
I mean, the Apollo missions, they weren't there for long, so the chances to encounter one of these quakes is rather slim.
I mean, they were active in 6 years, these seismometers were active.
Yeah.
And during this time, that's, first of all, very limited period of data. Yeah. But secondly, during this time, the strongest moonquake was 5.5 or 5.3.
Oh, yeah.
But this, of course, doesn't mean that the strongest moonquakes are the sizes. Maybe we were lucky and we have measured the strongest moonquake in the last millions of years.
Yeah.
Yeah.
You shouldn't expect that. Yeah.
Exactly.
You would expect that what hits you is mostly something average, especially, I mean, if you measure over 6 years, that's still not considerable, but what you encounter should be more average. It's just more likely that it was an average quake. Okay, because I didn't... yeah, but essentially what I meant was the Apollo missions were there for a very short time, so they did... Even if they would have known about that to that degree, to that extent we do today, they probably wouldn't have to worry about that much. I mean, especially if you're talking about a colony to put down some fixed structure with a fundament or something like that, then you'll have to worry about structural integrity, and then it becomes really relevant.
Exactly. Yeah, and also tectonics is a field where we can learn a lot, From earthquakes, we can learn from the interior structure of the earth, like what minerals are deep down on the surface, deep down beneath the surface. We can learn from that through earthquakes.
Yeah.
And on the moon, with like very new, nice seismometers, we can learn maybe even a lot about the interior of the moon that we have not known to that point. And so I think that's a field where there is just more science needed. We are very limited with our data. We have to, like in many sciences, of course, but it's like looking for data everywhere, just trying to pull out everything that we have, just to see if maybe there's one thing that could have led to an answer that we haven't thought about before.
Yeah. It's, I keep saying that, but it's amazing what people in planetary sciences do work with. You guys are mostly working from satellite data. Yeah, a broad array of satellite data, but I feel like a broken record, but yeah. Ground crews, people working on the moon, that's really what you would need to do really thorough geology. It's, just from the very limited experience we had and from what everybody has shown us during our bachelor's degree, geology on Earth is almost unimaginable without people working in the field. And I'm really looking forward to when maybe in our lifetime people work up there for more extensive periods of time.
Yeah, there's something that I dreamed for a very long time, just to at least experience somebody landing on the moon and on Mars. And so let's see, hopefully that will happen during the next years.
Hopefully.
Maybe. Yeah. So first of all, thank you that I was able to talk about this today.
You're welcome, I guess. I honestly, it's for me, it's the same as it was for you with the Balva episodes, that, I've been hearing about your project for a long time, and it's just, now it's this putting everything together, and you had me convinced that the moon is actually pretty interesting and still a kind of dynamic place before. And I hope that the listeners do see the moon differently now as well when they look up at the night sky.
That's something that I always try to engage, like people showing that the moon is not so boring as it seems.
All right. Anything to add? Anything you would still like to say?
Nah. I think I've talked long enough.
All right. So, once again, we haven't fixed on the next topic so far. So no announcements for next time?
Yeah. And with that, I wish you a very nice day or evening. And bye.
Bye, guys.
Thanks for listening to the RockyTerrain podcast. If you enjoyed listening to us, please consider subscribing on your favorite podcast platform. Everything addressed in this podcast reflects our own opinion. You can contact us at 4.5GAinthemaking@gmail.com. That is 4.5GAinthemaking@gmail.com. All music used is from Kevin MacLeod and was downloaded from filmmusic.io under the Creative Commons license. That is heavy interlude for intro and outro, and home bass groove for intermission.
Do you actually still need me? Or I think I can leave, can't I? Boring.
Gut.